I'll be focusing on binary black holes in this talk, although I will say neutron stars a couple of times. But for black holes, they're very simple. When we observe binary black holes, we pretty much just learn about their masses. So how big is each black hole? Just for notation, right, there's a primary mass, M1, which is the bigger of the two, and the secondary mass, M2, smaller one. Then we also learn how fast they're spinning and where are the spin axes pointing. So each black hole spin is this three-dimensional vector, and there's chi1 describes the spin of the primary black hole, chi2 describes the spin of the secondary black hole. Sometimes this is also written as A instead of chi, depending on context. And then third, there's we measure the distance to the binary, and this is what Rachel highlighted in her talk. Really, in my talk, I'll be using luminosity distance and redshift interchangeably, just assuming we know the background cosmology. Of course, in gravitational waves, we're actually measuring the luminosity distance. And then all of these things together tell us how black holes are made, as Michaela gave a great summary of in her talk. And just some more details about what we might learn about the origins of these black holes. So what were their progenitors? Likely they were massive stars, and so for this talk, I'll kind of just be focusing on that. Of course, there are other hypothesized progenitors of these black holes, like they could be primordial black holes made in the very early universe, but I'll be focusing on the stellar origin. And then if we learn what their progenitors are, we also learn where and when did these massive stars live, how did they die, how did these stellar deaths affect their environments, and then how did these stellar remnants actually pair up into merger partners and become gravitational wave sources. And all of these pieces of the story affect the masses and spins and merger rates of gravitational wave events. So the idea is that if we can measure the population of masses, spins, redshifts, all of that, we can then go back and try to piece together these pieces of the puzzle. And so for the next few slides, I'll just give an overview of how the population inference works, which we've already heard a little bit about, but just to make sure we're on the same page. The first step is to measure the parameters of the individual gravitational wave events. So this is the parameter estimation step, which we've learned a bit about yesterday, and we'll learn a bit more about tomorrow and later in the week. But I'll just skip over this. Basically, this parameter estimation step is really cool, and it gives us these posteriors over the event parameters. So this is just a very small section of a big plot from the third gravitational wave transient catalog, which appeared last week on arXiv from the LIGO-Virgo COGRA collaboration. And here you can see, right, for each one of these gravitational wave events, we analyze that data and infer a posterior distribution on the chirp mass, mass ratio, effective inspiral spin, effective processing spin, and luminosity distance, for example. And here, the height of these violins is proportional to the posterior probability distribution at that number. So like this event, GW191103_012549, probably had a chirp mass of like 8 solar masses. So that's the first step. And basically that parameter estimation posterior is here written as the probability of seeing the event i's parameters given the data for that event I. And so here theta I represents this multidimensional space consisting of masses, spins, distance, all of that. Fortunately, I think Salvo used theta I to denote single event parameters, and so will Coulomb. So we're consistent with that notation. So this, right, depends on the likelihood for that event times the prior divided by the evidence. There's some default prior that's assumed here. So here, H is the model, H for model, that describes this prior. But there's, in the parameter estimation results that I showed on the previous slide, this is just some default prior. The point of the population inference, or one of the points of the population inference, is to actually find the best prior, or some probability distribution p theta that is common to all systems. And so what we do is we go from single events to a population. And so now we're introducing some population model where H, instead of just being this fixed default thing that's like flattened masses, it's its own model with some population hyperparameters. And these hyperparameters now are describing the distribution of masses, spins, redshifts, and are common to all of the events. So an example, which Salvo also introduced in his introduction, is fit a power law to black hole masses. And so there the hyperparameters are the slope of the power law, the minimum black hole mass, and the maximum black hole mass. So that's just a simple example. Now this power law is common to all events, and we're interested not in what is the mass of GW19 whatever, but what is the power law of the mass distribution across all events. When we do that, we have to take into account measurement uncertainty and selection effects. So this is because for an individual event, we don't exactly know what its mass is, right? So there's some parameter estimation likelihood. What's the probability of seeing the data I from event I given theta I? And here, what we're interested in doing is finding this population model, again, this best prior that we should be using. And so we are multiplying the likelihood for event I by this population model, which now depends on our hyperparameters lambda. So this is an expression for the likelihood given the population model, H, and its hyperparameters. And here, this numerator looks very similar to like an evidence that I showed you a couple of slides ago. But it's not exactly that, because we are also conditioning on detection, which Rachel highlighted in her talk. So we're conditioning on detection, and that introduces this selection effects term beta, which represents the fraction of detectable systems in the population described by lambda and H. And so an example of selection effects is that a number of people have brought up so far, right, is that as we go to larger total masses of our binaries, our sensitivity to those increases. So this is in terms of the sensitive volume. And this is just because the larger binaries are intrinsically louder in gravitational waves. We can see them to a larger distance. So that's all this is. But this means that if we had a population where the maximum black hole mass was 100, then the overall sensitive volume to that population would be larger. And here we would downweight that population, right? So this serves to penalize populations that have these larger sensitive space-time volumes, or VT. And actually, the paper that this plot is from, that this plot argued that actually the fact that we were missing these big black holes in the population meant that there was a maximum mass cutoff in the population at around 50 solar masses, because otherwise we would have seen these bigger black holes. So that's just an example of why selection effects are important. Now, another piece to the population inference is that it updates our knowledge of individual event parameters, right? I kept saying that we're looking for the best prior we should be using in our parameter estimation of individual events. Well, actually, the population analysis is simultaneously updating our inference of what the individual events parameters are, as well as fitting the underlying population. So this is an example of that from an event, GW 170729, which used to be very exciting because it was our biggest black hole from the second observing run. Of course, now we've seen things that are much bigger and more exciting. But just to stick with this example, this was in orange. This is the default prior that we used in our parameter estimation to infer the source frame primary mass of this event. So under the default prior, it was most likely around 50 solar masses. But when we simultaneously fit the population, we could see that in the population at the time, there was very strong evidence for a maximum mass cutoff for a complete absence of black holes above around 40 solar masses. So our updated inference of this event's mass actually is almost definitely below 50 solar masses under that population. And same thing for the mass ratio, because we were updating our inference on the primary mass to lower total masses, and also there was a preference in the population for more equal mass ratios, we were able to get a much more informative estimate of what is the mass ratio from this event if we included all of the events, all the other events that we detected, and used that information to update our inference of these parameters. So that is just an introduction to some of the pieces of population analysis. In the next part of the talk, I'll just focus on 3 astrophysical lessons, and I'll highlight one lesson or so each about the mass distribution, the spin distribution, and evolution with redshift. So starting with the mass distribution, I think I said I would talk about the upper mass gap, but I changed my mind. So I'll be talking about the lower mass gap. And fortunately, Michaela gave a great overview of both of these mass gaps in her talk earlier. So just to briefly recap what we're talking about, here is the same stellar graveyard plot from Michaela's talk, where here we can see black holes in blue and pink, and neutron stars in orange and yellow. Some of them are gravitational wave events, and some of them are electromagnetic detections. But basically, this lower mass gap is an observationally proposed mass gap motivated before any detections of gravitational waves by just the fact that the electromagnetically detected neutron stars and the electromagnetically detected black holes seem to kind of separate, and there wasn't really anything in this region between the maximum neutron star mass at around like 2.5 solar masses and the smallest black hole that had been found at around 5 solar masses. And this was one very exciting aspect of now looking for this in gravitational waves is that when we have gravitational wave events, we can actually test to see if this mass gap is also there in the gravitational wave events, or if it's just kind of a property of X-ray binary black holes. And so one way of looking at this question of the mass gap is there a feature in the gravitational wave compact object mass distribution between neutron stars and black holes? So if you think about it, with gravitational waves, we really haven't found any like convincing evidence for tides in neutron star gravitational wave observations. So really, from the point of view of gravitational waves, all we have is masses. We have small masses and big masses. And if we fit some mass distribution to the full event list, including both neutron stars and black holes, is there actually something going on, some feature between neutron stars and black holes? So just from the first gravitational wave catalog, which included 11 events, we could say that, yes, there was some feature. And what we did was we fit this parametric model where we actually said, OK, we're looking for a feature that looks like this. It's kind of this dip with some height that starts at gamma low and ends at gamma high. Whoops. When this is now showing the fit of the data to that model, and we found that, yes, if you tried to fit a single power law all the way from the black holes to the neutron stars, that was a bad fit. There definitely was some feature between neutron stars and black holes. We couldn't really tell if that was a gap or not. But there was something there, but it was only 11 events. So now we have a lot more than 11 events. And what is really interesting about these is that they're not really filling in that low mass gap. Now, most of the events we have are not really probing the mass gap because of these selection effects. Again, we're very sensitive to big black holes, not so sensitive to little things down here. But we do have some of these events. We actually even detected some neutron star black hole systems. And this is a plot that Amanda Farah, who's a graduate student at UChicago, made in her paper that just appeared on arXiv, which shows that here these contours show 90% probability contours of all of the events up to O3A plus the neutron star black holes. And here in gray is where this mass gap might be, so between 2.5 and 5 solar masses. And you can see that we are not really filling in the gap. We're getting a lot of events that are kind of right on the boundary of the gap, and this one weirdo over here, GW190814, which seems to be like right on the gap, and we are still very confused about what it is. But we're not getting a lot of events in this gap, so this looks kind of suggestive. And Amanda found, when she kind of updated this fit, that even with these new events, we have a lot more events at low masses, there's still a clear deviation from a single power law. So we cannot fit one power law from neutron stars up to the lightest black holes at like up to 30 solar masses or so. And that deviation is at around 2.4 solar masses, which seems to kind of look like where the neutron star maximum mass is from other things we know about neutron stars. So that's kind of interesting and is starting to probe that supernova explosion mechanism or the boundary between neutron stars and black holes, which also relates to very uncertain nuclear physics, right? So here on the right is a bunch of other models that are now fitting the full event or the full mass spectrum all the way from 1 solar mass to cut off this plot, but like 100 solar masses. And this is from the LIGO-Virgo COGRA collaboration paper. And you can see that these are just different models. They tend to all agree that there's something going on at the low masses, although we can't really tell if it's a gap or a dip or what it is. But it definitely seems to be saying there's some separation between neutron stars and black holes, and that with more data, we'll be able to resolve that and learn more about the supernova explosion mechanism, for example. Okay, so moving on to the second astrophysical lesson, which is in the spin distribution. So I'll start with again, a brief summary of these effective spin parameters. So I think we've seen a plot like this a few times already. But right, we have a binary, and so when we talk about the spins, each black hole's spin is tilted perhaps with respect to the orbital angular momentum axis. They're each spinning with some magnitude, how rapidly they're spinning, and then some orientation. This effective inspiral spin parameter, chi effective, measures the total spin along the orbital angular momentum axis. So it's an average of the part of the spin of the primary here and the secondary here that's pointing in the same direction as L. And then the effective precessing spin is some measure of the spin in the orbital plane. And I won't really talk about this, but we heard yesterday that Lucy has done a lot of work on this. So if you're interested in precessing spins, you should check out Lucy's poster, perhaps. Okay, so I'll be talking a bit about the effective inspiral spin. And so kind of a first thing you could do is to just fit a Gaussian to this effective inspiral spin. And in this plot, it shows the inferred distribution of this effective inspiral spin in GWTC2 in black, or in GWTC2 in the dotted blue lines, and then the updated in GWTC3 in black. And so you can see that here it seems there's some preference for the peak of this distribution to be greater than 0, but it's also consistent with being centered at 0. And one thing that we are very interested in is, are there any systems with this effective inspiral spin being less than 0? Because that implies that there are spins that are misaligned by more than 90 degrees. And it's very difficult to get that misalignment if you think that the only way of getting misaligned spins in the isolated evolution channel is by supernova kicks. Because then you'd need a very big kick and it would disrupt the binary. So if there are a lot of spins with a chi effective less than 0, a lot of systems with chi effective less than 0, that would suggest that perhaps they're not all formed by isolated binary evolution. If the chi effective distribution is centered at 0, that suggests that the spin distribution is isotropic, and so it could all be assembled dynamically where there is no preference between different spin orientations. And so the current distribution seems to favor either a dynamical origin or a mixture between dynamical and isolated. Although I should say that making this measurement is very tricky if you think that there are a lot of systems with black hole spins almost exactly at 0. And I know Javier here had a paper about this with GWTC2, and so I'm curious to also see what that looks like with GWTC3. The other thing we can do is we can actually learn about the individual spin magnitudes rather than just these effective spin parameters. And Mikhail already showed this plot, but one thing that we're already learning is that for whatever reason, the spins in binary black hole systems are much smaller on average than the spins in both low mass and high mass X-ray binaries on average. And so this kind of remains a mystery right now and might point to some aspects in the evolution of the stars that are leading them to have these spins, which we don't understand yet. So finally, the last astrophysical lesson I'll talk about is this evolution with redshift. And what we can do is we can measure the merger rate as a function of redshift just by looking at where the distances of the events we see are, convert that distance to a redshift for ease of comparison with electromagnetic observations, and that gives us a merger rate density as a function of redshift. And so this is the latest fit to that from GWTC3, and you can see here the blue line here is the median merger rate density as a function of redshift that we infer, and the bands enclose 50% and 90% probability at each redshift. And then for comparison, the star formation rate is shown here in black. So we can already learn a lot by comparing our inference of the merger rate evolution to the star formation rate. And here is one way of doing that comparison. This is in blue, shows basically the same thing as before, but it's a little bit older. So this is the GWTC2 inference, and it's also normalized to the merger rate today to just focus on the shape of the merger rate evolution. And so in blue, again, is what we infer from gravitational waves. Here in orange is the star formation rate. And then if you assume that the progenitors of these binary black holes trace the star formation rate, but there's some delay time between the formation of the star and then the eventual merger of the binary black hole, those delay times, depending on what you assume, will lead to these curves here, these other colorful curves. As we go to longer delay times on average, you can see that this shape of the merger rate evolution becomes quite inconsistent with our inference because it just doesn't evolve as fast. Here, in all these cases, the peak is now moving to lower and lower redshifts or lower and lower look-back times, and the slope is not as rapid. So we're starting to rule out these very long delay times, again, assuming that the progenitors are following the star formation rate. And so here's one way of quantifying that by actually fitting a delay time distribution to the data directly. So this is a fit to that delay time distribution, just assuming a piecewise constant function. And you can see that there's a lot of support for pretty short delay times, shorter than 4 billion years or so. Actually, the data is consistent with no delay times at all, which you can see just from the fact that the merger rate evolution is consistent with the star formation rate. So the data is consistent with having no delay times at all. This does depend, again, on that assumption of the progenitors following the star formation rate. In reality, we probably expect the progenitors to trace the low metallicity star formation rate, which peaks at earlier redshifts because the metallicity of the universe is evolving. It was on average lower metallicity at higher redshifts, but that's, if you're interested in those details, you can check out this paper where we do look into that. And the reason this is interesting for several reasons that Michaela actually talked about as well earlier. But one reason this is interesting is because the time delay distributions actually directly relates to the physics by which these things are assembled in the first place. So depending on the physical processes that are going on to get these progenitor stars to form black holes and then merge, you'd expect different time delays. Those processes just take different amounts of time. And so here, I won't really go into detail into these plots, but these are just some plots that I collected from the literature that are showing predicted time delay distributions for different channels. So in this plot, for example, which is from a paper by Monica Gallegos Garcia, who's a graduate student at Northwestern, you can see that common envelope evolution leads to shorter delay times than stable mass transfer, for example, and we're still not sure, even within isolated binary evolution, whether systems are assembled through common envelope or without common envelope, which is just stable mass transfer. Here is a plot showing the delay time distributions for dynamical assembly in globular clusters, and you can see even within globular clusters, systems that are ejected have longer delay times than mergers that happen inside the cluster. This is a plot from the chemically homogeneous evolution, which actually favors much longer delay times. So this delay time distribution is already in tension with data. And here's an example from stellar triples, which has some common aspects to field binary evolution, but is also a little bit different and favors longer delay times. Okay, so those were the 3 astrophysical lessons that I wanted to get through. And in the rest of the talk, I just want to spend a little bit of time on some ongoing and future work, because everything I talked about so far has been fairly simple parametric models that are good for when you have like 10 to 100 events, which we are very rapidly outgrowing, because by the time we turn the detectors on again in 04, we'll have, like in a month, we'll already pass that 100 event limit, right? So gotta do some new work. And so the first thing I'll talk about is some model checking and outlier tests. And so the question here is, when do we have to upgrade our simple models? How can we know if our models are failing? And so a picture you can have in your head is Tyson's trash can picture from yesterday. If we fit a garbage model to our data, we're getting some inference about the population, but it's garbage. It's not actually describing the astrophysical distributions. And so one thing we've been doing a lot of in the gravitational wave population community is these posterior predictive checks. We also do model selection with like odds ratios and Bayes factors. But one advantage to a posterior predictive check is that you don't have to specify an alternative model. You can just ask, does my model fit the data? One disadvantage is that there's not really a single statistic you can get out of that and then use that to reject a model. You can pretty much just look at a lot of pictures, which is fun. So here's an example of a picture you can look at. And so here, the idea of a posterior predictive check is you're comparing your observed events, which here are shown in orange, to a predicted catalog you would get from your model. So you have fit your observed events to some underlying astrophysical distribution, and now you can use that to generate mock events, so to generate a fake universe and apply selection effects to that, and then generate that prediction and actually compare it with your observation and see if it's actually matching up to test whether your model is good enough, or also whether there are like bugs in your analysis and your sensitivity estimate is not good or something. But here, so what's shown here is that projection in terms of primary mass and redshift, and there are actually a bunch of catalogs here overlaid with each other, which is difficult to see, but there are different markers that correspond to different both observed events, because there's measurement uncertainty in our events, and predicted events, because we can generate many realizations from our distribution. And you can see here that the blue and the orange dots tend to be on top of each other. There's like, okay, there's nothing really weird going on with our model, except maybe here at high mass, and low redshift, where we are, according to our model, we should have some events here a lot of the time, but we really don't have any observed events here at high mass and low redshift. And this is from a paper with myself and a bunch of people in this room, actually, where we use this to actually see, okay, does this mean that we need to fit a more complicated model? Do we need to add redshift evolution to the mass distribution? Do we need to actually have a model that is able to predict the fact that we haven't seen high mass, low redshift events? And another way you can look at these posterior predictive checks, you can try to make plots like this, which show here this is the difference between the predicted and observed in just the primary mass as a function of the observed. And if the model is doing a good job of fitting the data, then there should be some fluctuations where we overpredict the primary mass. And there should be some fluctuation where we overpredict and some where we underpredict. And on average, we should kind of be getting the same prediction as the observed mass. And this is just splitting the data into low redshift and high redshift because this is from the same paper. We're looking at that same question. So you can see maybe something here is a little bit worrying, like at around 40 solar masses, we tend to be over predicting those events. And so maybe this feature is something that you'd look at and say, like, okay, maybe this model is not good. Like, what is happening over here in this posterior predictive check? But again, this is just a picture. You can turn these things into statistics, like you can count how many curves are over predicting versus under predicting. In this case, it turns out to be like 80%, so definitely not significant in terms of a p-value. But interpreting these things and like assigning a statistic to them is pretty difficult. If anyone has any ideas about how to make that better or more robust, also happy to discuss that further. The other thing that goes into this category is outlier tests. So I just wanted to briefly highlight some recent work by Reed Essick, who's there, and Colm and me and other people. So basically, another thing that we tend to do in addition to posterior predictive checks is maybe there's one weirdo event in our event list that we think maybe doesn't really fit the population. So one example of this is 1908-14, where we were like, well, it seems like it's too massive to be a neutron star, but doesn't really look like our other black holes, so what do we do about it? Well, we can do a leave one out analysis. We can infer our same parametric population distributions with 1908-14 and without 1908-14. And in this case, they end up looking very different. But this is kind of cheating because we've selected this event in advance, and we're only doing an outlier test with that event. And so one thing you could do is you could repeat a leave one out for every event in the catalog, but that is computationally expensive as the catalog is growing. And another solution that Reed proposed is to define a coarse-grained likelihood where you're actually putting the question that you're trying to address into your likelihood. And instead of just leaving out an event, you can say, well, say I've detected all these other events plus some event in this coarse-grained bin. And here you can see that even when you do that, you can then predict what should be the minimum secondary mass of the events in my catalog. You will get a distribution that is very different from the actual secondary mass of 1908-14. So this event is definitely an outlier from the binary black hole population. There's another similar kind of outlier analysis model checking thing that Javier had in a recent paper of his. So I think we can also talk about that at some point. Another thing I quickly wanted to mention is these non-parametric population models. This was something that a lot of people here have worked on, and that the LVK did for the first time in its recent paper included some of these non-parametric or semi-parametric population fits. In the interest of time, I'm just going to advertise Bruce's poster. You should talk to Bruce if you are interested more in how this is currently done. The last thing that we're starting to do is look for correlations between parameters on a population level. So most of the plots that I showed earlier were just kind of like fitting the primary mass distribution and then fitting the spin distribution as independent distributions. But you might wonder, like, does the spin distribution vary with mass? And this is an instant of like the chi-effective, this effective inspiral spin distribution versus the mass ratio. There seems to be an anti-correlation on a population level where if you look at nearly equal mass ratio things, the chi-effective distribution is centered at 0. And then if you go to more unequal masses, the chi-effective distribution shifts to larger values kind of away from 0. And this is, I already kind of talked about this earlier, but looking at the mass distribution varying with redshifts, you can ask, did black holes tend to be heavier a long time ago at higher redshift compared to today? And the answer is maybe, but not necessarily. Okay, so just for a summary, the astrophysical lessons I talked about, there are a lot more lessons in the data already and a lot more work by other people, but just for the purpose of this talk, I talked about the transition between neutron stars and black holes, the fact that binary black holes tend to be slowly spinning and have large-ish spin tilts, the fact that we can use this evolution of the merger rate with redshift to constrain the time delay distribution, and then some future prospects and challenges. I think there's a lot more work to be done on these posterior predictive tests and the outlier tests and how to interpret those. Also, the non-parametric population stuff is very cool, and there's a lot of ongoing work on that. And then also looking for correlations between population distributions, and just to continue that and all the things that I didn't really have time to talk about, but I think are important, and maybe Colm will also talk about some of them too, are simultaneously modeling the signal and the noise population. So a bunch of people here have also worked on similar things, but really we never really know if a gravitational wave trigger is an astrophysical event or if it's noise. If we put a very high threshold for detection, then we have a pure sample, but we're missing out information about the quieter things. Also, a big question is how do we actually interpret the population fits in the context of the theoretical models? Like, I can tell you that the power law slope is -2 of the black hole mass distribution, and there's a peak at 35, but what does that actually mean for physics? Another thing is including cosmology. We can also include the theory of gravity, the neutron star equation of state in these population models. So Rachel talked about cosmology. There's a lot of ongoing work about these other aspects. Also, we can leverage information from the stochastic background, which kind of relates to the first point there. And then also these systematic uncertainties, which I didn't talk at all about, but I'm sure our Friday speakers will have solutions for this. And then also just doing smarter parameter estimation, sensitivity estimation, making everything more computationally tractable. And I will stop there.